Road to Olympiad.
Welcome to RTO. Consider the following problem. Find all positive integer solutions xy satisfying x to the power of y is equal to y to the power of x minus y. For such problem, we can start by finding some obvious solutions, and using those solutions we obtain, try to observe if we can see any pattern there to generalize our solutions. Pause the video if you like to give this problem a try, and when you are ready, keep watching to learn how to solve it. To solve this problem, we start by considering the easy case when x is equal to y. This gives us x to the power of x is equal to x to the power of 0, which is equal to 1. Here we get one solution where both x and y are equal to 1. Next, we consider the case when x is greater than y. Usually, we need to consider the case when x is not equal to y, but we do not consider x smaller than y here because that will make the power x minus y a negative number, which gives the right hand side to be a fraction unless y is equal to 1. X minus y cannot be negative number because this will result in the right hand side to be a fraction, but the left hand side is still an integer. Also, it is not possible for y to be equal to 1, as x smaller than y will not give positive integer x solution. Back to the case of x greater than y, we can divide both sides of the equations by y to the power of y, which will give us x over y to the power of y is equal to y to the power of x minus 2y. Notice that x over y is greater than 1 because x is greater than y by the assumptions, so we have the left hand side is greater than 1. And since y is positive, this implies that x minus 2y must be positive as well. And this will imply that x must be greater than 2y. We need also y is greater than 1 in order for the result to be greater than 1, as well as y must divide x in order for the left hand side to be an integer. With this, we can let x is equal to ky for some positive integer k, and thus we get this one, which we can expand and simplify into this by dividing y to the power of y on both sides. Notice that the right hand side can be simplified as y to the power of k minus 2 times y. By observing the equations, we have k is equal to y to the power of k minus 2. And since y is greater than 1, or in other words, y is greater than or equal to 2, we have k must be greater than or equal to 2 to the power of k minus 2. We can easily check that k is equal to 3 and k is equal to 4 satisfy the inequality. If k is greater than or equal to 5, we are going to claim that the inequality is not satisfied, which is to say that k will be less than 2 to the power of k minus 2 in that case. Well, the claim is true when k is equal to 5 because 5 is indeed less than 2 to the power of 5 minus 2, which is equal to 8. If we assume that the claim is true for arbitrary k greater than or equal to 5, then k plus 1 is less than 2 to the power of k minus 2 plus 1. Notice that 1 is less than 2 to the power of k minus 2 for the given range, and the sum here is equal to 2 times 2 to the power of k minus 2, which is equal to 2 to the power of k minus 1. Thus, we have the claim is true for k plus 1 as well. And hence, by inductions, the claim is true for all k greater than or equal to 5. Therefore, the only integer solutions for k in which the inequality is satisfied are k is equal to 3 and k is equal to 4. And when k is equal to 3, we have y is equal to 3, which gives us x is equal to 9. And when k is equal to 4, we have y squared is equal to 4, which gives us y is equal to 2, and x is equal to 8. Hence, There are only 3 solutions for the above problem, which are 1, 1, 2, 8, and 3, 9. And this marks the end of our solutions. Post in the comment below if you have any thought on the video, and if you haven't subscribed yet, consider subscribing. This will really help us out. Anyway, see you in the next video. Thank you.